Okay, so diffraction basics. The double slit experiment was, it proved that A, an electron can be represented both as a particle and a wave, and B, when it is represented as a wave, it either undergoes constructive or destructive interference. So constructive interference is when two waves, their troughs and their peaks line up so that they produce a wave with a greater amplitude and greater intensity. Destructive interference is when the troughs and the peaks are exactly out of phase, so they cancel each other out and they produce just a horizontal line. And this obviously has very low intensity. So there was actually an experiment conducted by Tanimura. I'm going to show a video in just a sec, but he basically aimed many electrons at a slit, and the first few hundred electrons were just randomly dispersed. They kind of look like this. But then after a statistically significant number of electrons was aimed, they eventually started producing this pattern. More of them clustered here, some were here. And this pattern is actually just depicted the constructive destructive interference that we know. So this was like a darker line, and the darker line indicates destructive interference. So this showed that each electron does not carry phase information, but only many, many electrons do.
Now we are looking at the detector plane on the monitor. Bright spots appear here and there. These spots indicate individual electrons. Electrons are sent out only occasionally. Therefore, the chance of finding one electron in the microscope is very small, not to mention the chance of finding two. Since electrons are detected one by one as particles, we have to conclude that each electron must have passed through at random on either side of the biprism, thus creating a uniform distribution without any interference when accumulated. Under such condition do electrons form a uniform distribution? But look, we begin to see some fringes in the perpendicular direction that looks like interference fringes. Since this experiment lasted for more than 30 minutes, I have sped the movie up. Interference fringes are now clearly visible.
Okay, so now we're going to talk about scattering by a crystal. So a crystal just looks like this. So there's a plane A, B, and C. There's N1, N2 in the N2 direction, N3 direction. So this is composed of many unit cells. Crystal is just simply many unit cells. So that's why it's so easy to obtain scattering from, because you can obtain scattering from a single origin. And the total scattered wave is just the summation over all these unit cells. So if you draw this in an argon diagram, you have scattering. It can either be perfectly in the x-axis, T1. This just represents the scattering by one unit cell. And another one, it can be slightly out of phase. This can be T2 and can be displaced by 2 pi times the dot product of A and S. And I'll explain S. S is the scattering vector, which is perpendicular to the lattice plane. You can have another scattering wave T3. You can have infinitely many here. So this is why T infinity. So this is why you only obtain scattering from a crystal if all of these vectors don't cancel each other out. So if all of them point in this direction, or if all of them point in this direction. So this is why these three conditions must be met. So the dot product of A and S must equal an integer value H, and the dot product of B and S must equal an integer value K, and the dot product of C and S must equal integer value L. So these are known as the Lau conditions, and any crystal that diffracts meets these conditions. So now we're going to talk about Bragg's law, and we'll keep these here for proof later. Okay, So now let's say we're looking at a crystal from a bird's eye view. So you only see the 2D. This is A, this is B. So if you're reflecting planes like this, with distance D between them, then, and this is your scattering plane, which is always perpendicular to your reflecting plane, so it's S, it's a vector as well. Then your A direction, it's split into A over H. This is basically what defines a unit cell, A over H, and these all add up eventually to A. Similarly, in your B direction, each unit cell is defined by B over K, and these eventually all add up to B, similar in the C direction. So if you project the A over H vector on your S vector, you basically move this vector to align with this, you get 1 over magnitude of S, but this also equals D. So D equals 1 over S, and also you know that A over H dot S equals 1. Just from this, you can just rearrange these. B over K dot S equals 1, and C over L dot S equals 1. So here we know that, we also know from proof that the magnitude of your scattering vector equals 2 times sine of theta over lambda. So now we can show that, let me erase. Now we can show that because D equals 1 over S, and also that S equals 2 sine theta over lambda, that S equals 1 over D, so 1 over D equals 2 sine theta over lambda, and therefore let's just erase everything. Okay, 2D sine theta over lambda equals 1, which is Bragg's law.